Hi, my name is Chris Mason, and today I'm going to talk to you about Acceleware FDTD and some of the features and benefits that you would get by using Acceleware's FDTD software libraries. I'm a product manager here at Acceleware responsible for the FDTD libraries. If you only had a couple minutes to listen to this presentation, this slide is the summary of everything that we're doing in FDTD today. FDTD is generally becoming more widely used and distributed throughout simulation markets in all sorts of varieties, which would include areas like photonics, lithography, microwave, and electromagnetics. We're seeing many different flavors of CPU-only solvers that are reaching out to the market. Some of those are free, that would come from university-type organizations, and others are commercial and well-established codes that have been in use in industry for a long period of time as well. Even though Acceleware does and was the first to use GPU-accelerated FDTD codes, other organizations are starting to produce GPU codes as well, as people are recognizing the high-performance computing capabilities of these platforms and architectures. Some of the main advantages of choosing Acceleware's FDTD solver is our broad experience in electromagnetics, over 20 years, and GPUs. We've been working on the GPU platform for over 6 years, right from the beginnings of GPU computing. Our libraries are robust, fully tested, and are commercially used throughout a wide variety of industries. In terms of feature coverage, we support all major FDTD features and continue to upgrade and improve on our feature sets as the research and opportunities become available to do so. And finally, we do have the fastest solution on the market. It's highly optimized and tuned for the specific GPU architectures that are available today, including the Fermi architecture that NVIDIA released at the end of 2009. If you'd like more information about FDTD, you can contact us at either of the two email addresses listed on the slides in front of you. Digging a little bit into more detail about our background in electromagnetics and FDTD experience, we have 5 employees with master's backgrounds in FDTD and 3 PhDs, all in electrical engineering, with focuses in areas of microwave, RF, and photonics, and over 100 man-years of industry design and experience from the software engineering domain. In terms of GPU expertise, Acceleware was the first commercial application of FDTD on GPUs. We launched our first product in about 2004, and we've been shipping and improving on that initial release ever since. We've gotten widespread adoption, and people are using it. We've been running code for over 6 years on GPUs. We also have a very strong relationship with NVIDIA. NVIDIA is an Acceleware investor. They invested in our organization early on when they heard about our GPU initiatives in around 2006. Or at the end of 2006. And we have a great working relationship with them in the sense that we get the opportunity to help provide feedback on their products, so to generate new features on the GPUs that will benefit FDTD users. We work with them on bug fixes as well when they occur in their drivers. This product is also an extremely mature product. Because we've been shipping it and running it for so long, it's fully tested and debugged and actively maintained by our engineering team. On top of that, we have a large end user base who are using it on a very regular basis. And the next slide actually shows some of these end users. In the upper left-hand corner, you can see that that really addresses a lot of the cell phone manufacturers. Part of the design process of the cell phone is to actually model the antenna in advance of building a prototype. By building a simulation inside a computer, you can save a significant amount of time, effort, and money by modeling it first, making sure that you're happy with the initial layout, then moving it to the prototype phase. Most of these organizations have adopted antenna design simulation as a major or critical part of their design flow, and as such, slow simulations become a bottleneck in bringing their products to market. Acceleware has been able to offer our libraries to them so that they can use them to speed up their design flow. And we've actually found and heard great feedback from these customers in the sense that they have been able to take the antenna design modeling part of the design flow and it's no longer become critical path for them. They've been able to remove it from the critical path, meaning that they can spend more time either optimizing their design, so iterating over a certain set of parameters to get a better design, or it just shrinks the time to market, depending on their timelines for launch. Some other interesting customers on this list worth talking about include Kodak in the upper right-hand corner. They were our first adopter of GPU clusters, clustering of GPUs, so being able to have multiple compute nodes with GPUs attached to each compute node. Their application involved looking at CMOS image sensors in digital cameras and modeling the crosstalk or the bleeding between pixels. In this case here, the simulation size was very, very large, and it was prohibitive to run on a single node, and hence the need for cluster. And we were able to improve their simulation time by well over 10 times improvement, bringing their simulation times down from in the order of weeks to days or even inside days. Some other customers on this list would include companies like Boston Scientific and St. Jude Medical, who use our libraries to model MRI coils. And of course the military with their antenna design in the lower left-hand corner as well show some examples of other applications that our libraries are used. In terms of our FDTD feature set, we support all of the basic features that you would get in a software modeling package, which would include dielectric materials, thin wires, dispersive media like Drude-Lorentz-Debye, anisotropic materials. In terms of excitation, we support, again, a wide variety, hard and resistive excitations, a Gaussian beam excitation, and if none of those are of interest, you can, of course, manually set your own excitation in both time and space. In terms of the boundary conditions, we support a nice complex boundary CPML. You can specify the number of layers of CPML that you would have in your simulation, and of course some of the simpler boundaries, which include PEC, PMC, and some of the other first and second order absorbing boundary conditions, Murr and Higdon. We do have a lot of advanced features that I wouldn't classify as basic, which include things like plane wave excitation for normal and sine cosine incidents. We also have periodic sine cosine support. Also, more in terms of the hardware configuration, we support multiple GPUs per node, meaning that if your simulation is too large to fit on the fixed memory size of a GPU, you can add more GPUs to the system, and that will allow you to grow your simulation size. And if that's insufficient, then that's where you can start migrating your program or your simulation to a GPU cluster, of which our libraries also support. In the case where you actually have multi-GPUs or a GPU cluster, we also support GPU targeting. And what that means is that for a specific computer configuration system, you can target multiple simulations at the multiple GPUs. And the idea there would be that, again, if you're running the same simulation with a different set of parameters, so you're doing a parameter sweep, for example, you could run these smaller simulations on one GPU across the cluster. We also have lossy metal or surface impedance boundary condition support for more accurate metal modeling, as well as we're in the beta stages of doing conformal metals, so curved metal surfaces.